Hi everyone, I'm going to present to you the installation analysis of reinforced thermoplastic pipe in existing underground piping. As introduction, carbon steel pipes that are laid underground can go through adverse deterioration in the form of corrosion. Internal corrosion may cause a carbon steel pipe to prematurely reach the end of its useful service life before the intended design life. A rehabilitation solution for a corroded carbon steel pipeline using a viable and cost-effective installation method, in example reinforced thermoplastic pipe (RTP) installation, is vital to extend the pipeline service life. The RTP is pulled through the existing carbon steel pipeline at the site, which then acts as a passive conduit for the protection of the RTP. Problem statement. RTP installation is the most critical exercise in the installation campaign as the RTP is subjected to high tension, where the RTP is pulled through the existing piping system, which consists of straight and bent section. A design underestimation of loads could result in serious damage, while overestimation would result in high operating costs. An accurate or improved analysis method is vital for the RTP installation. Purpose of study. The RTP pulling tension shall be analyzed to ensure that the installation load is within the RTP design acceptance. To carry out a much reliable analysis method for the RTP installation, a proven analytical analysis is applied and compared with the actual pulling tension. For the methodology, RTP insertion analysis. Analytical approach by employing Euler's equation to analyze the RTP insertion in varied friction coefficient of 0.2 to 0.4. RTP pull-in calculation at the bend section takes into account the bending stiffness effect. The left figure below shows the RTP pull-in through bend schematic and the equation. Meanwhile, the right figure below shows the RTP bending reaction forces, schematic and the equation. Case study. A rehabilitation work was conducted by installing RTP in nominal diameter 300 underground piping in Bintulu Crude Oil Terminal, Sarawak. 160 meter length of underground piping consists of two 45-degree vertical bends and one 60-degree horizontal bend to be installed with RTP. See the figure below for the underground piping schematic. For the result, the pulling tension jumps at the bend section as it experiences the bend resistance force. The pulling tension increases as the friction coefficient increases, where the friction coefficient of 0.4 has the greatest pulling tension, followed by 0.3 and 0.2 respectively. Friction resists the relative motion of RTP surface and pipe wall sliding against each other, which increases the pulling tension. The figure below shows the comparison between the calculated pulling tension in varied friction coefficients between 0.2 to 0.4 and the actual values. Furthermore, actual pulling tension values in between the friction coefficient of 0.2 and 0.3. The data shows that pulling tension using friction coefficient of 0.3 is the optimal value to be used for the particular RTP installation analysis. The figure below shows the RTP insertion at the feeding point on the left side and the arrived RTP pulling point at the right side. As conclusion, from the above consideration of the analytical approach and the actual execution of the RTP installation, the following conclusions can be drawn. The effect of the friction coefficient between RTP surface and the pipe wall on the pulling tension could be understood. The larger the friction coefficient, the larger the pulling tension. The analytical approach that can well estimate the pulling tension by assessing the bending stiffness of the RTP according to the beam theory could be established. As future work, it is expected to perform more exploratory research on the RTP torsional effect on the RTP pulling tension, particularly on the bend section, as the twisted RTP could increase the bending stiffness. These are the references used for the study. Thank you.